Let's get started here. So today we'll talk a little bit about test number 2. We will continue with the cluster analysis section, and depending upon how far we get, we might talk a little bit more about project number 2. Please note that I have changed the due date for project number 2. So it's Friday, November 3rd at 5 p.m. It was November 1st before. I'm not for sure if we'll get through as much material as I would like to in time for you to complete the project, so that's why I decided to move back. So are there any questions before we get going here? Okay. So test number 2, here's a grade distribution that I posted to the course website for the discussion board. Average score was 81. 5 students with a grade above 80%, 4 below. Now obviously there are some students here that probably are not satisfied with their grades. Just realize that this test is 20% of your overall grade. That's not 100%. So, there's still a lot of other grades that are out there that you can get to improve upon your overall course grade. So please take that into account when you think about your test grade. Hopefully, though, that this test, if you're not satisfied with your grade, this test will give you an opportunity to think about, okay, am I preparing well enough for this class? What could I do better? And if you want to talk to me about it, I'd be happy to give you some suggestions as well. So when you take a look at your test, please make sure that you have, under review, you have all markup checked so you can better see my comments that are on the test. Let's go over some of the problems on the test. So number 1, we had this parallel coordinates plot for the different kinds of wheat kernels. Most students were able to get the plot right. Sometimes there was problems with the interpretation. Now when I look at this plot, I immediately see that there's a lot of green on the bottom of the plot. And so that's what I would immediately focus on. That it seems that these scab kernels tend to have low density, low size, low weight. But don't just focus necessarily on just, let's say, one of the variables. What we can, one of the beautiful things about these parallel coordinate plots is that we can see trends across the variables. So for example, we can easily see for size and weight that if I have a low size, I tend to have a low weight as well. And so those are trends that I would focus on here. I might also talk about how it seems like the healthy kernels can tend to have a higher weight than the rest. That doesn't mean every single kernel is always, for healthy, is always above sprout and scab, but we're seeing these trends that there's more of them that seem to be above that. And so that's what I would talk about in this plot regarding trends. Now, also later, then we need to start talking about outliers. And the thing that I think sticks out the most regarding an outlier is what I just circled there. By far, this one scab kernel has probably at least 25% higher density than all the other kernels. And it also tends to have it also has the highest hardness as well. And so that's where I would focus on for outliers. Now there are other possible outliers. We can see how maybe these down here, this here as well as potential outliers. We have this up here as well. And so there's multiple ways to answer the question, but you have to also justify your answer. In this particular problem, though, let me just make sure I got the problem right. You need to give the corresponding observation number when you're talking about these outliers. And that's important because you want to determine, well, which kernel in this case is actually an outlier. You know, it's nice to say, yeah, there's an outlier. Well, what is the actual observation? And so you need to actually identify that corresponding observation. And there's a number of different ways to do it. I show one particular way in the answer key here. Another way that one could approach it is, let's say, you know, you read in your data and you do a summary of the data, and you see for density, the highest density is 2.03. So whatever observation number that corresponds to, that's the max. Okay, so there's the 2.03 right there. So how would I again find then that particular observation number? Well, how about we just simply look at all the density values. We find 2.03. And it's right here. And that corresponds to, if you count, number 55. So that will be one way, probably the easiest way, to find, well, what corresponding observation number that is. And, you know, what I show then, you know, I go a little bit farther, you know, what I show then on this plot is, well, let's take a look at observation number 55. You don't have to do this additional plot, but it's helpful to do something like this in actual practice. And we can see not only is it the highest density and hardness, but it has about the smallest size and it has the smallest weight. So, you know, this is multivariate. This is a multivariate course, multiple variables. We can see that definitely this particular observation is sticking out from all the rest. That's the definition of an outlier. Now, you could have, you know, again, mentioned some of the other observations as outliers too, and I wouldn't take off points for it, but this is the one that really stuck out to me that I was hoping that you would see. Alternatively, you know, I mentioned in the problem description, well, you could also take a look at a star plot. And, you know, if I just look through these star plot, you know, one thing that just really sticks out is this one right here. Now, it's something that you have to be a little bit careful about in terms of how this labeling is done. This is actually for number 55, but unfortunately, it's a little bit harder to see that number there because there's it's actually printed on the star spot right below it. Okay. So number 2, I think this is an example of sometimes, well, we actually just saw one of these. This is an example where you got to be careful. You make sure you read the entire problem and look what the problem asks. So, you know, previously for that outlier, sometimes students were missing actually identifying what was the actual observation number. In number 2, the first part said state and interpret the corresponding principal components. Sometimes students would miss the state part. Sometimes a few, maybe 1 or 2 students miss the interpret part. But you got to state it, you can actually write out the equation, and then interpret it. And so, unfortunately, then some easy points were missed there because the whole problem wasn't answered. But in number 2 here, let's see here. So I have this plot of the principal components that I gave you. And obviously, one thing really sticks out compared to everything else. And in this particular problem, I asked, where is it? Basically, identify a feature of this plot that can also be seen in that parallel coordinates plot in number 1. And I really, really like this problem because it helps you make connections between the different kinds of plots that we've talked about. I mean, even when we talked about in the graphics section, the connections between plots, and eventually then the principal component section, we try to make those connections. And so that's what I was trying to assess there, if you can make those kinds of connections. And so with this plot here, again, that feature that I have arrow pointed to really stands out. And so you might be thinking, okay, well, how, if something stands out that much, how can that be represented in the parallel coordinates plot? Well, then that gets into understanding this has a large principal component number 2 value. So principal component number 2. In order for it to have a large value, I need to have a large density. I need to have a large hardness. Okay? This particular value has a large density, has a large hardness. And so that's what you could have focused on in this particular plot to talk about. I saw it was an outlier, it was a density. Very large density, very large hardness. And I see it in this principal component number 2. So that would have been the easiest way to do to answer that problem. And while it wasn't needed, some students decided to go ahead and do one of these plots as well. And one thing that you can talk about in this particular plot is that notice the green there for the scab. Notice how that kind of is separated to some respect from the rest. Well, that corresponds to what we saw for the parallel coordinates plot with respect to the density and 2 of the other variables as well. And so you could have talked about that. Okay. Number 3 was the factor analysis problem. Again, you got to state the factor analysis model. And some students do not do that. But let's talk about how to decide on the number of principal components. So are 2 common factors appropriate to use with this data? Some students, and this is what I would start off with as well, but some students chose to start off with the likelihood ratio test. Some students chose not even to do a likelihood ratio test, but start off with the likelihood ratio test. That's a great place to start. Take a look at this p-value. So the null hypothesis is that 2 common factors are sufficient. The alternative hypothesis is that you need more. That's kind of a low p-value. And so from that, you would say, well, I'm a little worried that maybe 2 factors are not sufficient. I mean, it's a borderline. If I had 0.05 as my alpha, 2 would not be sufficient. If I had alpha 0.01, then you would say don't reject HO, and perhaps 2 are okay. But you at least have to go through that logic. And if you immediately say 2 factors are sufficient because the p-value is 0.02 and leave it at that, you didn't get full credit. Because someone, again, could use alpha 0.05. And you would reject HO. Now, if you start talking about that there's marginal evidence that helped you get more credit, but we have other tools available to us to make a judgment. And so, since I have kind of a borderline decision here with this likelihood ratio test, I definitely would want to look at something else, the residuals. And if you look at the residuals, we have just 2 that are a little bit larger in absolute value than what we would like, but they're not too much larger. And so with that, I could probably, I could justify, yeah, okay, 2 factors, 2 common factors probably will work fine. It's not perfect, though. And so that's what I was looking for in that particular problem. And then lastly, 4B, let's talk about trellis plots. What about trellis plots allows us to plot multivariate data? And the answer actually came from essentially the right when trellis plots were introduced in the notes. And the key is you need to say something about conditioning. Trellis plots allow you to condition on particular values of our variables so that then we can look at the relationships between some of the other variables. That's the key with these trellis plots, the conditioning aspect. Okay. So that's all I had to say specifically about the tests. Now, if you have a question about why I took off a certain number of points on your test, please ask me that individually after class. I'll be happy to talk to you about it. If you have a question, though, about how to do a particular problem on the test, after you've taken a look at the answer key, if you still have a question about it, please feel free to ask at this time. Were there any questions about how to do particular problems on the test? Okay. Let's move on to cluster analysis again. So the purpose of cluster analysis is to basically have a formal way to group observations. And these observations aren't grouped in any previous way that you know about. So for example, like with the goblet data, we don't have based upon the information that we've collected, we don't have a grouping. But as you will see eventually, we want to come up with some kind of grouping. This grouping is called a cluster. So a group is a cluster. It's just a name that has developed over time. And so, how do we make decisions about what observations to put in the same cluster? And so you would think that, well, it has something to do with some observations being, let's say, similar to one another or dissimilar. The ones that are similar you're going to put together in the same cluster. The ones that are dissimilar, you're going to keep them as separate. So how do we measure similarity? There's actually a number of different measures. We're going to talk about just the most widely used ones, and that is Euclidean distance. So you can think of this, if we have just simply two variables and we plot data in a scatter plot, if we just actually essentially like put a ruler down on the plot, essentially that's the Euclidean distance, if the ruler is properly scaled. And so we could do the Euclidean distance just with the irregular data or with the standardized data. In almost every application, people will be using the standardized data. The reason being is because you don't want, let's say, some variables that are measured in a different numerical scale than other variables to have an actual effect on what you say is similar or not. There are some special cases where you still want to use just plain old Euclidean distance, but generally speaking, most people will use standardized Euclidean distance to take out the fact that some variables are measured on different scales. And so once we have this way of measuring how similar observations are, then we can use one of a wide variety of different cluster analysis methods to put the observations into groups, into the clusters. There are three main different, let's say, categorizations of cluster analysis methods. Today we are going to focus on what's called hierarchical, and hierarchical is split up into two different parts, where today we're going to focus on agglomerative, where the basic idea is this. Every observation, the process to find these clusters is hierarchical, meaning that there's a number of steps involved to determine what observation goes into what cluster. And so in an agglomerative method, what we do is we assume, let's say if I have 10 observations, I'm going to start off with 10 clusters. Every observation is its own cluster. And then what I'm going to do is I'm going to look for the two, let's say, clusters then that are most similar. And then I'm going to merge those two clusters together to form a new cluster. So now I have, if I start off with 10 observations, 10 clusters, now I'm going to have 9 clusters. Then what I'm going to do is, based upon these 9 clusters, look at the ones that are most similar to one another using some kind of measure like the a variation actually of the Euclidean distance. And I'm going to put those two clusters together to form a new cluster. So now I could have just 8 clusters. And I'm going to keep on going in this process until all the observations are in just one overall cluster. You might be thinking, oh, wait a second. Why would we want to have just one cluster? Well, one of the big things that we're going to be talking about is one of the big things that we're going to talk about is how do I make a decision about where to stop the clustering process? Maybe once I get to 3 clusters, I want to stop. Maybe I get to 5. I want to stop. How do I make that decision? That's what we're going to be talking about. Okay, so now we're going to get to new material. With the agglomerative clustering, there's actually a number of different ways to actually implement it. We're going to talk about a few of them. Why are we talking about a few of them rather than just focusing on the best? Because there is no best method. And so we're going to begin with what's called the nearest neighbor method, also referred to as single linkage by some people. And here's the process, kind of similar to what I just described. Let's say I have n observations. Every observation is going to be a cluster. So clusters of size 1. Then I'm going to merge the two clusters together that are the nearest to one another. And in the end, it's just simply, well, which have the smallest standardized Euclidean distance. Then, so I have 2 observations that are in a cluster. Then I'm going to need to somehow then make a decision about, well, what's going to be merged next? And the key is that how do you make a decision about how do I measure then the distance between this cluster that has 2 observations? How do I measure that distance that cluster is from the other observations? How do I do that? And the way that this is done, and we'll go through a simple example shortly. To find the distance between this new cluster and the other observations is the minimum distance between the 2 points in the cluster and the other observations. So now I have all these distances again, and I need to decide, okay, well, I need to now merge a set of clusters again. And so I put the 2 nearest clusters now into a new cluster. And I continue this process until everything is in one cluster. But the key is, at some point, and we'll get to it eventually today, I'm going to need to figure out, okay, I don't actually want to go to just one cluster. I want to stop somewhere before then. Okay, so here's the example. I have simply 4 observations and only 2 variables. It's an easy example to help illustrate this. And we're just going to use regular old Euclidean distance. We're not going to use standardized Euclidean distance here. So what I need to do to begin with is find all possible distances between each of the observations. So for example, if I want to do observation 1 and observation 2, which equivalent we can think of as, at least right now, cluster 1 and cluster 2, I can find my Euclidean distance by taking the 2 to the 3.4. I'm going to put that into my x1 vector. I'm going to take the 4 and the 5, put that in my x2 vector. do the matrix multiplication, and I get 2.56. Here's a nice plot that helps illustrate this. So I have the variable 1 and variable 2. Variable 1 is on the x-axis, variable 2 is on the y-axis. I have the actual variable numbers nicely labeled there as 1, 2, 3, and 4. And so we had just found the distance between observation 1 and 2, which was 2.56. So I drew a line there to say, hey, I'm going to find a distance, and I put the actual distance typed in here. Okay? So these are all my distances between the observations. And the way then that we start the clustering process. Let's see here. I have it right now. Yeah. Sorry, I am jumping ahead here. I need to find the observations that are closest to one another. In other words, again, the clusters that are closest to one another. I'm going to join them together. So you look at all those distances that you see there. Well, what's the smallest distance? Well, it's the distance between 3 and 4, distance of 2.24. So that's my new cluster. So now I have 3 clusters. A cluster with just observation 1, a cluster with just observation 2, and now a cluster with 3 and 4. Now the clustering process continues. I need to decide, well, which clusters am I going to merge next? What the nearest neighbor method says is find all the distances between the clusters. And that's what I've done on page 12. Right here. So the distance between the cluster that has just 1 in it and the cluster that has just 2 in it, as well as just the distance between 2.56. But what's the distance now between the cluster that has just observation 1 in it and the cluster that has 3 and 4? What the nearest neighbor method says is look at all the distances and find what that minimum distance is. So the distance between 1 and 3, come up here, the distance between 1 and 3 is 4.02. The distance between 1 and 4 is 2.44. So the distance then that cluster 1 is to the cluster that has 3 and 4 in it is 2.44. Nearest neighbor. Observation 3 is the nearest neighbor to 1 when I compare 1 to the cluster that has 3 and 4 in it. That's where the name comes from. Now, what about the cluster that has just observation 2 in it? Well, let's look back at the plot again. The distance between 2 and 3 has a distance, the distance between 2 and 3 is 2.83. The distance between 2 and 4 is 3. So the nearest neighbor to 2 is observation 3. And so the distance between 2 and the cluster that has 3 and 4 in it is 2.83. So, based upon what I see here then, well, what is now going to be the next cluster formed? It's still the minimum value in terms of the distances between the clusters, and that smallest distance is right there, 2.44. So now, get a new one here. Now for my second stage of my clustering process, I have a cluster that has just 2 in it, and then a cluster that has 1, 3, and 4 in it. Okay? Now the next step, I need to decide, well, what am I going to merge next? Well, it's going to have to be 2 with 1, 3, and 4, but let's think about the distances. What would be then the distance between the cluster that has 2 and the cluster that has 1, 3, and 4 in it? What will be the distance? 2.56, because that's the minimum distance. 1 is the nearest neighbor to the cluster that has just 2 in it. Okay, so that's how it works. Let me come back up here some. Sorry that I skipped around a little bit. So top of page 10, I just show you in R how to do the actual math. If you were to find then the actual distance between observation 1 and observation 2. Fortunately, there's a nice function in R called dist that will find all distances between your observations. So how did I use it? Suppose I create, let me remove the grammar check here. That's kind of annoying. Okay, so I create a data frame called set1 where the first column is going to be for var1. I just put in all the variable 1 values. Second column is going to be var2, put in all the variable 2 values. That's going to go into a data frame called set1 for the lack of a better name. And then I say dist, first argument, x equals set1. What kinds of distances do I want? Here I just want Euclidean distance. So I put that into an object called dist.mat for distance matrix. It's not actually formally a matrix, but it just made sense to do that. And this is what I get for all those distances. Some people refer to this as a lower triangular matrix, even though R is actually not recognizing this as a matrix class. And so to make sure you understand how to read this, so the distance between observation 2 and 1 is 2.56. Notice we do not have well, let me skip that. The distance between 3 and 2 is 2.82. Now notice I do not have a distance between 2 and 3. Why? Well, because it would be exactly the same. Whether I'm looking at observation 2 versus 3 or observation 3 versus 2, it doesn't matter. It's still the same distance. So that's why you see those empty spots in that structure. Now to actually to do my plot coming up, I need to transform this into something that R actually recognizes as a matrix. And the way to do that, there's a function called as.matrix, meaning treat it as a matrix. So if I do as.matrix of dist.mat, and I just put it back into an object with exactly the same name, now I do have an actual matrix. And the reason why that's important is because I can actually access a row and a column to pull out the different distances. Okay? Now, how did I do that plot? Depending upon your interest in knowing, understanding this code, I will go into more or less detail. So what I do here is I first use the plot function, where on my x-axis I put variable 1, y-axis variable 2. Let me actually just come over here. And we're in the plot. There it is. So I begin by plotting the simple points. I have a big blue circle there. How do I get the blue circle? Well, I say color equal blue, plotting character equals 16. If you go back to the intro to R notes, you'll see that what's often called a filled circle or closed circle is plotting character number 16. And then I use CEX, where is it? Yep, CEX equal 5, meaning make the plotting point 5 times larger than the default. Okay. Now, to get the actual lines and the distance is actually shown on the plot. So the red lines, and to actually plot the distances there that you see, I need to use some for loops. Now, in many programming languages, there are like for looping structures, there's do looping structures. R uses a for looping structure here. And so what I do for each possible, let's say, how should I put it? For each pairwise combination of the variables, let's say variable 1 and, for each pairwise combination of the observations, let's say observation 1 and observation 2, observation 1 and observation 3, observation 2 and observation 3. What I'm going to do is use the segments function to draw a line between the two blue dots representing those observations. And then right in the middle of that red line, meaning like kind of like a halfway point, I'm going to plot the actual distance. I'm going to actually plot the numerical value of the distance. And I do that through two for loops. And so this is what I'm going to ask you here. Would you like me to go through this for looping structure here? Or are you comfortable enough with for loops that I can skip it? It's up to you. I'm happy to go over it some more. Okay. Okay, let's. So I have two indices here, I and j. Is this big enough, or do you need me to make it bigger? Big enough? Okay. Two indices, I and j. And what this is going to correspond to first is that I is going to be for observation 1, j is going to be observation 2. And so if I just highlight this code, okay, so for example, here's I is equal to 1. And then I'm going to use the segments function to draw a red line between observation 1 and observation 2. The way that the segments function works is that imagine you have, oops, I have 2 points on my plot. One is going to be at, let's say, x sub 0, y sub 0, in terms of the x-axis and the y-axis. Another point is going to be at x1 and y1. And so in the segments function, I specify x0. And so what that's going to be is the first variable value for observation 1. Okay, it's equal to 2. The y0 component is going to be for the second variable value for observation 1, 3.4. x1, y1 is now going to be for that second variable. I'm sorry, the second observation, excuse me. The line type is going to be a solid line. It's going to have a color of 2, which R translates into red. And the line width is just 1, meaning it's just the default. I didn't actually need to put that. So if I run this segment of code, what you're going to see on the plot is the red line. So it took the 2 points in our two-dimensional space, drew a line between them. Now I'd like to actually put in here what the actual numerical value of the distance is. And so I can do that using a function that we've seen before called text. Where do I want to plot the actual numerical value? Well, what I'm going to do is find the average between variable 1's, the value for variable 1 for observation 1, the value for variable 1 for observation 2. That value is 3. That's going to be on my x-axis. My y-axis is going to be the average between 3.4 and 5. So 4.2. Why am I doing this? Well, if you look at the plot, that should mean then I should be like, if you see where my mouse is, I should be right about here where I draw my text. What's the actual text? I want the actual numerical value. And so that's where I go into my dis.mat. I get row 1, column 2, which is the actual distance. I put that as my labels argument for the text function, and I round it to 2 decimal places so that it just looks nice. And so when I draw that out, there we go. Now I like to be able to repeat this process for now observation 1 and 3, observation 1 and 4, observation 2 and 3, and so on. So this is where the for loop comes in, where I say for I in 1 to 3. I use a curly bracket, if you can see what's highlighted there in red. Everything inside those 2 curly brackets is within that for loop. Then I say for j in I plus 1 to 4. Everything inside the curly bracket is within that for loop. So I have nested for loops. And so the first time that I run this segment of code, I is going to be 1. What's j? 2. Okay? And so I is 1, j is equal to 2, and I'm going to get exactly what I had just drawn before. Then you get to the bottom of the for loop, and then it's going to come back up here and say, okay, well now I need to go j equal to 3. So it's going to do for I equal 1, j equal 3. Then it's going to come up here and sees, okay, I still have j equal 4 to deal with. So now I have I equal 1, j equal 4. And then it gets down to here and says, oh, okay, I guess I'm done with that for loop. Now I'm going to go back up to my original for loop. And now I is going to be incremented to 2. So now I'm going to do this for I equal 2. J will be 3. And I keep on doing this process over and over again until I went through the entire for loop. And now I get all my red lines. I have all my distances. Last thing I need to do is I need to plot the actual observation numbers. And I use the text function to allow me to do that. The labels argument is just simply, well, the numbers 1, 2, 3, and 4. Color is white. CEX equal 2, meaning we're going to make it twice the default in terms of size. And there's my plot. Any questions? Okay. Now, there is another way that you can find these distances. The function that I just showed you, the dist function, is within inside the stat package. There's also a package called cluster, and sometimes people will use this. There's a function called daisy that will find those distances as well. Okay. Now, as I told you, there's many different agglomerative methods out there. Nearest neighbor, also called single linkage, is just one of them. And again, there's multiple ways to do this because none are perfect. Or none is the best, I should say. The problem that nearest neighbor can have is it can have what are called, it can form in the end what are called elongated clusters. So maybe during the clustering process, you get to a point where you have these 3 clusters and for some reason you decided to stop. Again, we'll talk about how to make that decision later. And so what we have there is labeled one elongated cluster. Now in this particular case, that elongated cluster seems fine. You know, again, we're trying to find similar observations and put them into groups, clusters, and indeed, it looks like we have 3 distinct groups there. I just wanted to show you what an elongated cluster looks like. Now, in another situation, you know, maybe you might have something like this. let's say we have these observations, what can happen is this. And this isn't necessarily drawn to scale the best. But we have two clusters here. They're elongated, as you can see. They're kind of stretched out. When that's what nearest neighbor might conclude, but if we look at this another way, maybe we should have this instead. Well, why does this happen? Why does nearest neighbor perhaps result in those red clusters there? Well, it's because of how nearest neighbor works. Through this hierarchical process, observations are joined to particular clusters. And the distances between the clusters is always the shortest distance between, let's say, this cluster and this cluster. And that's what, it's almost like a chain link. If you think of like a chain, I'm holding up a chain, if you can imagine a chain here, where you have different links together. It only takes, let's say, one close observation to link different, in this case, clusters. And so because of that, you can end up having these elongated clusters like this. It doesn't look at the whole necessarily. It's not like a one overall measure of distance between, let's say, a cluster that has 5 observations here and 5 observations here. Rather, instead, you're looking at the closest one here, you're looking at the closest one here to make that judgment about how you're deciding what's the distance between the cluster and how you decide what to join. And so because of that, you can have these elongated clusters. So you might be thinking, okay, well, rather than looking at the nearest neighbor, how about we look at the furthest neighbor? The observations in 2 clusters that are farthest apart, we're going to define that as the distance between 2 clusters. And you could do that. That's called the furthest neighbor method, also known as complete linkage. So before we had single linkage, that name comes about that, it just takes 2 close observations to make that decision complete. Basically, now you have to look at all your observations in each cluster and then pick the 2 observations that are farthest apart to make that. So you're looking at all the observations. You're looking at the complete cluster to make this judgment. So let's talk about how this works. So we're going to, look at this example again where we have these 4 observations. Here are the 4 distances. Now, this is where things can get confusing for students at times when they first see this. The measure of similarity here is Euclidean distance. And I'm always deciding between which clusters to put together by looking at the smallest distance between the clusters. So in this particular case, if I start off with 4 clusters, observations 3 and 4 are joined together. Now, where this name of furthest neighbor comes into play is next when I decide which clusters to join. So the distance between 1 and 2 is still 2.56. But now what's the distance between 1 and this cluster that has 3 and 4 in it? This is where furthest neighbor comes into play. Before, with nearest neighbor, I had min there. Now I'm going to use max. So the distance between the cluster that has just 1 in it and the cluster that has 3 and 4 in it is the maximum distance between 1 and 3, 1 and 4. That maximum distance is 4.02. When I compare 2 to 3 and 4, that maximum distance is 3. So now I have this table of all these distances. How do I make the decision about which clusters to join? Well, again, we're looking for the most similar. The smallest distance now that we see here is 2.56. So observations 1 and 2 now have just formed a cluster. Where students get confused then at this step is they say, oh, I'm using furthest neighbor. So that means observation 1 and the cluster has 3 and 4 in it should be joined. No. Where this name nearest neighbor and furthest neighbor come into play is when you make a decision, how do I measure the distance between clusters? You always still join the clusters that are the closest together. It's just how do you define distance? Any questions about that? Because this is a critical thing for students to understand. Any questions about that? So I'm happy to re-explain.
Can you repeat that plot again? Yeah.
Sure. Okay. Let's actually go back to our plot here. Let's see here. Because these are simple concepts. Nearest, furthest, but it can be just. Come on, my eraser's not working here. We'll just do it a different way. Okay, we'll try this. There we go. We'll try this one more time. Okay, so let's walk through this again. So, I have 4 clusters. I have the distances between all the clusters actually on this diagram. This is the smallest distance, so I'm going to join them together. Oh, man. Let's try something else. Let's go to my whiteboard. All right. So here are my clusters at this stage. Because the cluster with just 1 in it and the cluster that has just 2 in it have just 1 observation apiece, the distance between 1 and 2 is 2.56. But also I need to define what's the distance between 1 and the cluster that has, let's say, 3 and 4 in it. This is where the name furthest neighbor comes into play. I look at the distance between 1 and 3. I look at the distance between 1 and 4. The distance between 1 and 3 is the largest. So I'm going to define the distance between the cluster that has just observation 1 in it and the cluster that has observations 3 and 4 in it as 4.02. With nearest neighbor, I would have defined that distance to be 2.44. Now the distance of, let's say, 2 to the cluster that has 3 and 4 in it is 3. So the distance between 2 and 3 is 2.83. The distance between 2 and 4 is 3, so that distance is 3. Because I'm using the furthest neighbor method. So I have 3 distances here. And I need to decide, well, what's going to now be joined together? To make that decision, I still look at, well, what's the smallest of those distances? That smallest one is 2.56. So now, geez. I don't use whiteboard that often, so sorry. Take a little bit longer than I would like. So now I have those two clusters. So now, of course, the next what would happen is the cluster with 1 and 2 in it's going to be joined with 3 and 4. But my question to you is, what is the distance between the cluster that has 1 and 2 in it and the cluster that has 3 and 4 in it? Is that 3? What?
Last week.
Oh, I'm sorry, what? I'm looking at actual numerical value for what is the distance between 4.02. That's the distance. Okay? Because again, we're looking at what's the furthest neighbor of this cluster that's 1 and 2 in it to the cluster that has 3 and 4. What's the furthest apart they are? And so that's how you make that judgment. Let's see here. Yeah. As you might expect, this method is not perfect. It can be distorted by outliers. So you can imagine, let's say, one cluster, let's actually do a plot here. I think my computer's just having some difficulties here. So suppose we have two kind of compact clusters, but then we also have one outlier in one of those clusters. And you can see how that's going to distort the distances between these two clusters, because I have this one thing that's far apart. And so that can cause them problems about trying to find observations that are similar to one another and put them into nice clusters. So that's why this isn't a perfect method. So you might be thinking, okay, well, we've talked about the furthest neighbor. We've talked about the nearest neighbor. Is there something that we could do in between? Yeah. There's something called a centroid method, where if I want to find the distance between two clusters, I simply find the mean value for a particular cluster, then find the mean value for another particular cluster. The distance between those two clusters then is the Euclidean distance between the two cluster means. And so you think of a mean as being in the middle. So that's why I say it's kind of in the middle between furthest and nearest. We're looking at the distance between the two cluster means to make a judgment of, or then to find then the distance between the two clusters. So let's take a look at an example of this. Here are the distances that we have for that 4-observation example again. Once again, we're trying to find what's the smallest distance. That distance is 2.24, so observations 3 and 4 are going to be joined together. Excuse me. Now, I need to figure out, I don't know why I didn't draw a table like that. So 3 and 4 have been joined together. But now I need to find the distance between the cluster that has just 1 and then the cluster that has 3 and 4. And so what that means then is I need to find then what is the central point of the cluster that has 3 and 4. In other words, find the mean between observation 3 and observation 4. And so a simple way to do that is that here is observations 3 and 4. I use the column means function to find just now the column means when I just have observation 3 and 4. So that mean is 5 and 2.5. Okay? So now I need to find, well, what's the distance between observation 1 and something that has 5 for variable 1 and 2.5 for variable 2. And so one quick little way that I did this was I took my first 2 observations that are in set 1, and then I combine it with those column means that we just found. And so that now I have, let's say, a new little data frame that has all the values that I want to find the distances between. So I can put this back into dist, and this is what I get. So the distance between, let's see now, 1 and the cluster that has 3 and 4 in it is 3.13. The distance between observation 2 and the cluster that has 3 and 4 in it is 2.69. I look at all those distances. I find the one that's the smallest. It's at 2.56. So observation 1 and observation 2 are going to be joined now to a new cluster. So I have one more stage. Of course, the cluster with 1 and 2 in it is going to be joined with the cluster that has 3 and 4 in it. How do I find the distance, though, between those 2 clusters? Well, I find the mean for the cluster that has observation 1 and 2 in it, find the mean that has the cluster that has 3 and 4 in it, and I just simply find the Euclidean distance between those 2. That's how you do it. Okay. So that's one way to think about, being in between furthest neighbor and nearest neighbor. Here's another way. We can use what's called the average method. Now, note we just found some averages. So you have to be very careful about these names and what they actually represent. This is a different way of finding averages now. What we could do instead in this particular case is how about we look at all the distance between, let's say, this cluster and this cluster. Look at all those distances and find the average distance. So maybe I have, a total of 10 different distances between these 2. Just find the average of those distances. And that's going to be now the distance between this cluster and that cluster. So, let's go through the steps. So again, I start off with this table here. Observation 3 and 4 are joined together because it's the smallest distance. Now, to decide what I'm going to join next, distance between 1 and 2 does not change. The distance between observation 1 and the cluster has 3 and 4 in it. Well, what I do is I find the distance between 1 and 3. I find the distance between 1 and 4. The average distance then is 3.23. In a similar manner, I find the same way of finding the distance between 2 and the cluster that has 3 and 4 in it, and I get 2.915. Again, the smallest distance here is 2.56, so I'm going to join cluster 1 and 2 together. In the end, I'm going to have a cluster with 1 and 2. I'm going to have a cluster with 3 and 4. what's the actual distance then between these two clusters? Come back up to my, I'm going to come back to the whiteboard. That's not working. Let me get to the eraser. So I need to, so this is the two clusters I have. And I need to find now the distance between these two clusters. What would I need to do? The average distance, but basically all the numbers that you see on here for all these distances, well, let me put it this way. I think this is easier. I'm going to highlight the distances that I would use to find that distance. So I would take the average of those highlighted yellow numbers. I would not take the distance between 1 and 2 because that's already one cluster. I would not take the distance between 3 and 4 in this average because it's already one cluster. It's all the distances between the observations in the two clusters. Those are the ones that are average. So the average of that would be my distance between the two clusters. Any questions? Now overall, using the average method, using the centroid method, you can often have more, let's say, compact clusters than what we saw with the single link, with nearest neighbor single linkage. You have these elongated clusters. Obviously outliers are not going to be playing as much of a role, so you're not going to have the problems that furthest neighbor can have. And so those are some advantages of using the average method, the centroid method. But you might be thinking, well, why don't we just use those then, since you just talked about averages? Well, maybe there might be times where you want something like that, okay? And the average method and the centroid method might not work as well in those situations. So what ends up happening in practice, what you typically do is you use more than one clustering method, and then using some tools, then you're going to use some tools to make a judgment of, do these clusters make sense? So just to give you an idea of what we will do, is that we'll use principal component analysis to find some principal components that account for a large percentage of the variation of the data, plot the scores, and then also, let's say, for the plotting point, have that correspond to the cluster. Like if it's cluster 1, is it cluster 3, is it cluster 5? And look at the principal component. Think of if you have two principal components, think of a scatter plot of the scores. And if the observations are nicely grouped, then okay, you're satisfied with that clustering method. If they're not, maybe you have, let's say, two observations that are really close to each other on the plot, but yet they're in two different clusters. Then that calls into question, did this clustering method work well? We'll get to that. Lastly, there's another, sometimes you see this used, I see this used a lot less. Another clustering another way to do agglomerative, it's called Ward's minimum variance. And here you just redefine how you do the distance between the clusters by using this. N sub A is the number of observations in cluster A, N sub B is the number of observations in cluster B, and then we have corresponding cluster means, similar to like the centroid method, and some people will use this. On page 19 of my notes, I just basically took a table that is from one of the recommended books for this course that talks about a lot of the stuff that I just talked about in terms of comparisons amongst the methods. You're welcome to take a look at that.
I have a question on the third point. You said finally we join the two clusters together. Well, I understood that with the averages, we took the averages for like
We took the averages of those yellow.
Yes, so now, how do we, like, decide whether to join them or not to join them? Because the averages, are we going to look at maybe the smallest average or the biggest? It's like two separate clusters.
Yes, I guess I say stay tuned for that. I will talk about how we make that decision. Would we actually want to do it? But the way that these clustering methods will work is that you will go all the way to having just one cluster. And then once we've done that, then we go back and think, okay, did I really want to go to one? Maybe I should have stuck with two. Okay, so we will get to that. I'm going to get ahead of myself here. Okay. I guess I can talk about this here. You know, when we're looking at tables like this, where we have these distances, you know, you would expect that as you go from you know, or in our case, we had 4 clusters, then we go to 3 clusters, then we go to 2 clusters, then we go to 1 cluster. You know, you would expect that these distances between clusters would increase as you get to a smaller number of clusters. And that makes sense, especially for like single, for the nearest neighbor method. Because as you're joining clusters, now the observations are going to be farther and farther and farther apart as you continue to reduce the number of clusters. Some of these methods, though, can have what are called reversals. What that means is that the distances can actually decrease as you go from, let's say, from 3 to 2 clusters. Compare that from 2 to 1. The distance from 2 to 1 could be smaller than it is from 3 to 2. That seems counterintuitive. But because of how these distances between these clustering methods, or the distances between clusters are actually computed for like a centroid and an average, that can actually happen. I'll talk more about that later. As I'm going through my notes here, now actually doing this in a class, it's like, well, maybe I should have held off on that, but we will hopefully come back to that and see a nice plot that shows how that can happen. Okay. So the next part here is determining the number of clusters. And then we'll get to the question about, well, maybe I should just stop at 3 versus go to 2. Going through all these methods has taken a lot longer than I anticipated. And we're about at the end of class right now. So next time we will talk about how do I decide how many clusters I actually want. So let's take a look at then what's next for our course. So I have office hours after our class. Thursday we will continue with cluster analysis. Again, project number 2 has been moved back 2 days. And then just looking farther ahead, test number 3 is Thursday, November 30th. So, are there any last questions? Okay, and that's it for today.